So it looks like we have a few premature spring break casualties, but let's carry on. So remember, last time we were talking about paging and segmentation. So remember, paging is basically the OS's view of memory, which is some linear array of bytes. And so to basically lay out how things are stored in physical memory, we're using the idea of paging, dividing memory into fixed size pages, and mapping them onto the same size frames in physical memory. And we can do that in any order. Versus segmentation was where we're taking our process and we're thinking of it in terms of logical segments. So these are the sorts of things that the compiler is talking about. Things like the heap, the stack, the actual code of the program. These are all logical segments. And so then we're just combining paging and segmentation by taking each one of those segments, individually paging it. And so in doing that, we get essentially the benefits of both paging and segmentation that we're interested in. So up until now, we've basically been assuming that all of the virtual address space of a process is actually being mapped into physical memory, right? And this imposes certain restrictions, like you can't run a process that has more virtual memory than physical memory that's actually available, right? So essentially, today we're going to talk about how we can relax this assumption. And we're going to do that by using this idea of demand paging. So essentially, the idea is we're going to now use disk as a backup for actual main memory. So we're not going to impose that all of a process's memory is actually stored in memory. Some of its pages may actually just be stored on the disk. And so in some sense now, the main memory is almost acting as a cache for disk. Now, of course, disk is much, much slower than main memory, so we're going to have to be careful about how we do that. But that is going to give us flexibility that's useful. Will allow a process to actually look like it's larger than physical memory, right? So we've talked before about how one of the roles of the OS is to sort of present an illusion of having an infinite amount of resources, right? So this is sort of how we're going to do that with regards to memory. We can sort of present every process as if it has an unlimited amount of memory to use. And because we're storing everything on disk, you might have maybe a few gigabytes of memory. You might have a terabyte or even more of disk. So effectively, your disk storage is more or less unlimited. So also this will give us some other benefits, such as will allow a process to execute even if it's not entirely contained in memory. Right? So that'll be useful if we want to, say, start up a process more quickly. We don't actually have to load it all into memory before we can actually start executing it. And then, of course, it's also going to let us, because we now sort of have the illusion of infinite memory, we can run more processes at once. So actually, just quickly, we can actually see this. So these are the processes running on my system. And so we can look at both real memory. This is the actual amount of physical memory being used by each of these processes. But then we also have virtual memory. And in many cases, we see virtual memory is significantly higher than physical memory, right? So like this is like an instant messaging application that has something like 3 times the amount of virtual memory as physical memory. So all of its address space is not actually sitting in memory. So we're using much less to actually run that process. So the main idea here is, why can we do this? Well, remember, the main reason we can do this and have it not be terrible for performance is sort of the idea of locality, and this goes back to the 90-10 rule we talked about. Remember, when we're expecting that when we're executing processes, they're only using, almost all of the time, a small part of their actual memory space. So we can actually have the rest of the process be potentially sitting on disk, and we can still execute the process with only that small bit actually in memory, and it's not going to incur too much of a slowdown. So the way we're going to do this is we're going to have the page table. We're going to augment the page table a little bit to essentially say if the page is actually sitting in memory, right? Because now a page is not by definition somewhere in memory. It might be in memory somewhere in some physical frame, or it might be in no frame at all and just be sitting on disk. And so when we actually need to use a specific page, when we make a reference to a memory location in some specific page, if the page is not in memory, if it's sitting on disk, we need to actually go fetch it and bring it into disk. Now, because going to the disk is so slow, we're going to need to ensure that almost all references are going to be in memory. So we really need to keep it to an absolute minimum the amount of time we spend going to the disk. Right, and so this is again the idea of locality, where a process is working on a certain amount of its memory. So we might call that the working set, is essentially the small bit of the process that's actually being used at that time. So the working set may change over time. A process could, of course, at various times use all of its memory, but at some specific time, we're only generally going to be expecting a process to be using the same reasonably small working set. So we'll keep that in memory, and the rest of the process can potentially be sitting on disk without too much of a penalty. So essentially what this is going to look like is this, right? So now we have the page table, and sometimes the entries in the page table are pointing to actual physical frames in memory, but sometimes they're not, and we actually have to go to the disk. And so, if we reference, this particular page and it's not sitting in memory, we have to go to the disk, read that page off the disk, store it back into physical memory, and then we can actually, start using it. So, basically what I've just described is where we're just going to load pages on demand. Right? Because if you request a certain page of memory, if you're trying to access a piece of data that's in a certain page, you obviously need to have that specific page in memory at that time. So if you don't have it then, you're going to have to go get it from the disk. Now that isn't the only way we could sort of decide to load pages. Right? So there's some other choices we could make. So sort of the choice we've been implicitly assuming up until today is that when you start a process, you're just going to load all of its pages in. Right, that's one approach, and that is easy and it will work, but then you introduce restrictions. The virtual address space obviously can't be larger than physical memory if you're just going to go load in the entire process when you start. You could take some other approaches. You could, for example, have the application programmer say when they want to load and unload pages from physical memory. So, you could do that, but that's probably going to be very error-prone and not something that most programmers are going to actually want to deal with. And you could potentially have the OS or the process essentially predict when it's going to need a page, or actually have the OS predict when it's going to need a page and fetch it before the page is actually needed. So, essentially, the demand paging is what I already have talked about, where the first time you reference a page, that's when you're going to go fetch it. Now, this is going to introduce some additional complexities, right? Because you do have actually a finite amount of physical memory, right? We're trying to get the illusion that you have essentially infinite, but in practice, you have some fixed amount of physical memory that you can't exceed. So if you go try to reference, if you start referencing pages, pages are going to be brought into memory on demand, and at some point, you're going to actually fill up all of the available physical memory you have. And so when that happens and you request another page that you don't currently have in memory, you're going to have to go get that page, bring it into memory, and that's going to actually replace some page that's already in memory. Right, so this is the idea of page replacement that we're going to talk more about. Now, while you're actually going and getting a page from disk, you're actually also the process that is requesting that page is going to give up the CPU. And why is it that we're going to give up the CPU when we're going to fetch a page? Any ideas? So how long is it going to take to go fetch a page? Yeah. Right. You're having to go to disk. So that's potentially going to take quite a while. So whenever you're actually doing that, the currently executing process is actually going to give up the CPU. So this is the idea of what's called a page fault. So when you request a page and it's not sitting in memory, you have to go to disk. That's what's called a page fault. So that basically is going to trap to the OS. You're going to have to go get the page from disk and give, the currently executing process is going to give up the CPU while the page fault is being dealt with. So now we could consider this idea of pre-paging where, you're not just going to do it on demand. Maybe you could have the OS guess in advance what pages will be needed and load them into memory so that when the process requests them in the future, hopefully you already have them in memory, right? Because sort of the whole bottom line in all of this is page faults are very expensive. We don't want to do them. We want to do them as infrequently as possible. So, if you can guess correctly what pages you'll need before you actually need them, then you can load them into memory, and then once you need them, they're already there, right? So that'll allow us to do more overlap of CPU and I/O. But of course, if you guess wrong, you can still run into page faults. And if you're guessing wrong, you may actually evict memory that's actually useful, right? Pages that are currently in memory that you're having to throw out, you might actually need those pages. So, pre-paging is a nice idea, but in practice, it's often going to be, fairly difficult to do. So, let's talk about how we can actually implement demand paging. So, first of all, we're obviously assuming that, the whole program is going to be stored on disk, right? Because that's sort of the baseline for where everything is sitting, right? All of your program, your code, your data is all sitting on the disk, because that's where you're initially, going to be loading it from. Right, and with demand paging, remember, we're basically using the disk as a backing store for memory. So, of course, if something isn't in memory, the obvious assumption is that you can go get it from the disk. So, of course, everything is going to be sitting somewhere on disk. So, we're going to have this extra bit in the page table that indicates whether each page is in memory. So, if the bit is 1, that means it actually is in memory. If it's 0, then that could mean that either it's either sitting on the disk, or you could potentially be accessing a bogus entry in the page table that's not actually valid. But you can essentially just assume that that means we need to go to disk to get it. So when we actually reference that, then we need to fetch the page from from disk rather, right? So that's a page fault. And so, the OS then needs to decide what page we're actually going to replace when we bring that new page in from the disk. So, once we've done that, we obviously are invalidating the existing page. We're going to the disk, reading the page, loading it in, and again, we're giving up the CPU while we're doing that, right? Because that's an I/O operation, could take quite some time. So we're going to context switch to some other process in the meantime. Once that process has actually been loaded in from the disk into memory, we'll get some interrupts. We can update the page table entry to indicate that the page is now sitting there, and then we can essentially continue with the process that actually caused the page fault. So essentially, of all these steps, the one that's sort of most interesting is how we actually select a page to replace. So we'll talk in more detail in a little bit about how we can actually do page replacement. Now, one thing we haven't actually talked about is sort of where you're actually storing pages when they're not in memory, right? Because they need to be on disk somewhere, but we haven't actually said where we're going to store them or how. So this is basically the idea of swap space, which is that's an area of disk that we're going to be used for storing pages of memory, right? So when you normally consider how you're storing data on your disk, right, you're normally talking in terms of like a file system or files in a file system, right? That's what your data on disk is. But your swap space may actually not be part of a file system, right? Because it's essentially just some region of the disk that the OS is using to store pages of memory. So those aren't necessarily part of the file system. So actually, we can I can give you a quick demo of that. So various OSs might do this differently, but for example, on Linux, there's basically often a dedicated partition that's actually being used for swap space. This is your swap partition. So for example, on this Linux system, there is some partition on the disk. It's not a file system. There are no files in it. It's just a region of the disk that has been allocated to the OS just for storing pages of memory. Now, you could use this on the file system. So, for example, my system is a Mac, obviously. And in general, on a Mac, you don't actually have a swap partition. You actually do have, in the file system, you have these files, which are your swap space, right? So on my system, there's this directory, internal to the OS, where there's a bunch of these files, and swap file 0, 1, 2, 3, we see that these are each order of a couple hundred megabytes each, right? And so those are just binary files that the OS is actually using to store pages of memory into. So it's just reading and writing in those as it's doing demand paging. So essentially, at any given time, we have pages of memory that could be in potentially, the file system, or physical memory, or swap space, or some combination of the three, right? So there's a number of different places that pages could exist, right? Because remember, originally everything has to be, sitting on the disk somewhere. When you start up a program, you're typically starting it from a file on disk. It loads into main memory, but as it gets swapped out, it may, end up in swap space. Now, there's one nice little sort of optimization we can notice, which is, suppose we're considering pages of code from an executable, for example. So anyone see how we might be able to optimize those when we're considering how to use swap space? Yeah. So that's a good point, that if you're doing something like pre-paging, when you're running through OS, when you're running through program instructions, it might be fairly easy to predict the next page you might need. So that's a good point. But how about when you need to, say, throw out a page of code, right? So you've got a page of code in memory, and you've decided to, replace it with some other page. Normally what you're going to do is you're going to write out that page of memory to the swap space, right? But what might you be able to do with a code page? So how is a code page different from, say, a page of the stack or the heap? So are you ever actually changing a page of code? Yeah. Right, exactly. Right, pages of code are never changing. You're never actually, changing those pages while they're loaded into memory. So what this means is that you don't actually need to put those pages into the swap space. Right, you can basically just use the disk directly as the backup. Right, because if you're swapping out a page of code, you can just essentially throw out the copy, and whenever you need that page in the future, just go grab it from disk again. Right? You can't do that with something like a page of a heap, because that is changing in memory. So when you need to put that out, when you need to throw that out of memory, you need to store it in the swap space so that you actually have a record of whatever changes are made, so that when you load it up in the future, you'll still have those changes. People see how that works? So essentially, read-only pages, you can essentially just use the file system and not actually have to use the dedicated swap space. So you'll have to, use less swap space and do less disk I/O to actually, do demand paging with something like code pages. So now let's talk about how we can actually, what sort of the performance impact of demand paging is. So let's say that we're going through and accessing pages, and let's say that P is the probability of getting a page fault. So that's some probability from 0 to 1. That's the probability that whenever we request some address, it's going to cause a page fault. So what determines the speed of a page fault when we're actually executing this? Right, so what are we having to do on a page fault in terms of performance? What is the operation your computer's doing? Yeah.
How long it takes to go to disk, find the page, and read that?
Right, so it's basically determined by your disk access time, right? Because whenever you're hitting a page fault, you're having to go to the disk and read the page in. Right, so that's going to be determined by how fast your disk is. And that's potentially very, very slow, much, much slower than memory. Now, when we don't have a page fault, right, then that's going to be essentially the same memory access time we remember we derived an expression last class, which was basically, a memory access time plus some overhead for the TLB and possibly up to 2 memory accesses if we get a TLB miss. Remember we had some expression for that saying, if we got a TLB hit, it's just the memory access plus a little TLB overhead. If we got a TLB miss, we have to go to the page table and then to memory itself. But let's just ignore all those details for the moment and just essentially assume that if you don't get a page fault, then it's just the price of going to memory. So typical. So essentially the effective access time now is going to be whenever you get a page fault, it's going to be the page fault time, which is going to disk. And then whenever you don't get a page fault, which will be 1 minus p of the time, it's just going to be the price of a memory access. Now, to give you some typical numbers of what this might actually be, memory access might take maybe 200 nanoseconds to go to memory. That's sort of a typical value. Whereas going to disk, your disk response time might be more like 20 milliseconds, which is about 5 orders of magnitude slower, way, way slower. So then that gives us, an effective access time, something like this, 1 minus p times 200 nanoseconds plus p times 20 million nanoseconds. So now let's suppose that, right, so obviously it's clear from this that whenever we're hitting a page fault, it's going to take a lot more time. So we're obviously going to have some amount of performance penalty from actually doing demand paging. Because whenever we're getting these page faults, we're taking a lot of extra time. So, let's consider, supposing we're willing to pay maybe a 10% penalty in our effective memory access time in order to do demand paging. Right, so if we're doing that, if we're willing to pay a 10% price, then we can essentially ask the question, what is our allowable page fault rate? Right, because as the page fault rate is higher, your effective memory access time is getting worse and worse. So we can actually calculate this directly, right, because we can essentially just say, if we want the effective access time to be 10% slower than a direct memory access, then we can just say, 1.1 times the regular memory access time is going to be equal to this expression, remember, which is in terms of the page fault rate that we just defined. Right? That's the effective memory access time when we're doing demand paging. And if we're willing to be 10% slower than just directly accessing memory, then we have this expression. Right, and this is a simple expression that just has one variable. We can just directly solve that for the page fault rate. And in this case, it's going to be 1 over 100,000. So what does that mean? That basically means that in order to take no more than a 10% hit in your memory access time, only 1 in 100,000 memory accesses can actually incur a page fault. Right, so this sounds like it's really bad, right? Because if 1 in 100,000 seems like barely any page faults at all. That sounds like it would be very difficult to actually achieve that. But remember, the reason this is still feasible is because of that 90-10 rule with locality, where almost all of the time, you're accessing the same small number of pages repeatedly. So because of that, you're not sort of accessing pages randomly all over your process's address space. You're going after the same small set of pages repeatedly, so almost all of the time, you're actually not getting a page fault. Right? So page faults are actually very, very rare in practice. So, a page fault rate on the order of 1 in 100,000 is not actually unrealistic. So that's why we can actually do demand paging without getting a horrible slowdown in our effective memory access time. Questions on that? Okay. So remember, now we have extended our page table with a bit that's saying whether each page is in memory. And now remember, the page table is potentially large, so that's stored in memory, and we're using the the TLB as a cache so that we don't have to repeatedly do memory lookups in the page table. So now we're going to use the TLB a little bit differently when we're actually using demand paging. So the TLB now is also going to indicate whether a page is in memory. So when you get a TLB hit, what that now means is both that the page was in the TLB and also that the page was in memory, right? Because a TLB hit, if the page is not actually sitting in memory, essentially does you no good, right? You've avoided a memory access, but you have to go to the disk, which is so much slower than memory, it essentially doesn't even matter. So, on a TLB miss, essentially the OS is now checking if the page is in memory. right? Because that's now separate from the issue of whether it's in the TLB. So if the page is in memory, then we're essentially just doing what we did before. We're just going to pick some TLB entry, replace it, and now we're done. Right now it's in the TLB. If the page is not in memory, then we essentially are picking a TLB entry to replace, but then we're also having to do the page fault operations. So we're invalidating the TLB entry, grabbing the page from disk, and then updating the TLB entry, and then finally we're restarting whatever instruction caused the page fault. Right? Because when we tried to execute the instruction that caused the page fault, we weren't able to do that, and we suspended the process. So that instruction was not able to complete. So once the page fault has been serviced, we're going to rerun that instruction that actually caused the page fault. Right? And this is still completely transparent to the process. Right? The process doesn't know that paging is going on, doesn't know that pages are being swapped in and out of the disk and memory. Right? It's just executing as normal, and on page fault, it's getting suspended while its pages are being brought in, but the process itself doesn't need to know about any of that. Now, this sounds like it's maybe not sort of a big deal because we sort of outlined all the steps, but there's actually still a little bit that we have to be careful about, largely in terms of when we're going to restart the instruction that faulted, that caused the page fault. So, the question is basically, how can we actually transparently restart a faulty instruction? So this is not always trivial. So let's consider, say you have an assembly instruction like this, which is a real assembly instruction in some architectures, where we're going to say, we're going to move we're going to first take some register value, R10, we're going to decrement it, pre-decrement, and then we're going to move that value into memory address A. Right, so let's say we're executing that assembly instruction. And let's say that, the address A causes a page fault, right? Because any time we access a memory address, we could potentially cause a page fault. So what's essentially the problem here if that caused a page fault? If we're executing this instruction, we're decrementing the register, then we cause a page fault, so we suspend the process, handle the page fault, and now restart the instruction. So what's the problem? Right. Remember, what we're doing here is, the first thing we did is we decremented that register value. And then we tried to move it into a memory address and caused a page fault. Right? So essentially, this is an instruction that has a side effect of modifying that register value. And if we just sort of naively re-execute that instruction a second time, we've potentially decremented that register twice. Right? And so if we do that, then the page fault is no longer transparent to the application, because the process register's value has been decremented twice because of that page fault. Right? So essentially what we need to do is we need to be able to unwind whatever side effects we caused in that instruction before we actually hit the page fault. And that's a fairly simple example, right? You could consider, well, how do you unwind, subtracting 1, just add 1, not anything too interesting there. But in some cases, this might actually not be so trivial. So, for example, there are some assembly instructions that basically let you do bulk transfers of pieces of memory. So basically, you can say, take a block of memory starting at this address, going to this address, and copy it to some other range of addresses. Right? And there are basic assembly instructions that can actually let you do that. So anyone can see what might be the problem if you start executing an address like that. Executing an instruction like that. How might that cause side effects and then cause a page fault? Anyone have any idea? Right, so these blocks of memory could be any size. Right, so what potentially could happen if the block of memory you're copying is very large? Yeah. Right. Basically, this block of memory that we're copying from could span multiple pages. So you could have a block of memory that's, half in one page and half in another page. So what could happen is, the first page might be in memory. So you start copying that and overwriting other memory with that data, and then you hit the second page and that's not in memory and you get a page fault. Right? And here, you essentially can't, easily unwind what just happened because you already have essentially overwritten memory, right? So there's no way that you can actually recover the memory that you've already overwritten when you hit that page fault. So essentially here you'd have to do something more complicated, such as basically checking before you do an operation like this that all of the pages you're going to be touching are actually in memory. And so then, do the page fault before you actually try to execute the instruction so that you don't end up with side effects that you can't undo. All right, so bottom line here is basically just that, the idea of a page fault is, conceptually simple, but it does introduce some added complexities with our processes of, how can we actually do things like restart an instruction without having change, while keeping it completely transparent to the process itself. Questions on that? Okay. So now let's talk about the major thing that I've mentioned a few times, which is how we actually want to choose pages to evict. Right? So the idea here is that, remember, you have a fixed amount of physical memory, and as you're requesting pages, you're bringing them in from disk on memory. And remember, you no longer have a restriction on how many pages processes might have, because you can essentially store any amount on disk. So as you're bringing in pages, at some point you're going to have filled up all your physical memory. And now you're going to request another page that's potentially on disk, and you need to bring that into memory. Since memory is full, you need to actually choose an existing page of memory to replace. So we need some algorithm to actually do page replacement. Now, why is how we actually do page replacement important? Anyone have any idea? Yeah. Right, exactly. So the point is that if you evict a page that you're just about to use again, you've essentially just forced yourself to have a page fault, in the short term. Right? So if you have a bad page replacement algorithm that you're evicting useful pages, then in the future, you're going to need to go back to the disk and get them back, and that's going to be more page faults, right? And the whole point is that we need to keep the number of page faults to an absolute minimum. Page faults are extremely expensive. So essentially, the way we can measure if a page replacement algorithm is good or not is by simply saying how many page faults does it incur, right? So if a page replacement algorithm minimizes the number of page faults, then that's very good. If it causes a lot of page faults, then that's very bad. So we're going to look at basically 3 different types of page replacement policies. So the first one is FIFO, first in, first out. So the idea here is that, right, you're just loading in pages one at a time, right? So you've essentially got a sequence of pages that you've loaded in from memory. And whenever you need to load a new page, you just throw out the oldest page that you loaded. Right? So if you've got 3 pages of memory, A, B, and C, you load A, you load B, you load C, and now let's say you load a 4th page, D, and that causes a page fault, what are you going to throw out? Right. A was the oldest page you loaded, so you're just going to throw out A. And then the next page that causes a page fault, you're going to throw out B, so on and so forth. You're just throwing out the oldest page. Question?
Yeah. So say you use you load A, you load B, you load C, and then you load A again. Would A stay where it is, or would it move?
Right. So we're sort of, in that case, we're assuming we basically have 3 pages of memory, 3 frames of memory, right? Because this is all determined by the amount of physical memory you have. So let's say you have 3 frames of physical memory. You load A, B, and C. You now have memory containing A, B, and C, right? Because you had 3 frames of memory, so you can store 3 pages. Now if you go and load page D, that's a 4th page. You don't have a free frame to store that page in, so you have to evict something.
But if you use A after C has been loaded?
So you're saying if you loaded, say, A, B, C, and then A again?
Yeah.
Well, so in that case, the current contents of memory are A, B, and C. So if you reference A again, that's not a page fault, right? Because A was already sitting in memory.
Well, yeah, but because of that, if you call D again, if you call D after the second A, would A go away or would B go away?
A would still go away because first in, first out is when we're just throwing out the oldest page that was loaded.
So even if it was used more
Yes, exactly. And that is a good segue into the other policies. So the second policy is min, I assume because minimum number of page faults is where that means, also sometimes called opt. So the idea here is that we are going to throw out the page that we're not going to use for the longest time. Right, so what's the idea here? The idea here is that you get a page fault when you are using a page, when you are accessing a page that's not in memory. So in order to get the fewest number of page faults, you essentially don't want to access that page for the longest time. So this policy is actually provably optimal when you just throw out the page that you're not going to write. So when you're picking a page to evict, you have some set of pages sitting in memory, and of them, you're going to pick the one that's going to take the longest time until you need it again and throw that out. So that's provably optimal, but what's the problem with actually doing that? Yeah. Right, exactly. This, again, requires knowledge of the future of what you're actually going to predict. So what we can consider instead is a third policy, LRU, least recently used. So this is basically going to approximate the min policy, and we're going to assume that the past is a good prediction of the future. So what that means is that if I, say, just used a page, if a page was the last thing I accessed, then probably it's not a good thing to evict, right? Because if I just used it, then because of locality, there's a really good chance that I'm going to use it in the near future as well, right? Versus a page that I haven't used in a long time, chances are I'm probably going to continue to not need that page, so that's a much better candidate. So hopefully you're all having flashbacks of CPU scheduling, because what does this sort of remind you of when we were talking about CPU schedulers? Yeah, right. So remember in CPU scheduling we had, shortest job first, which was sort of the provably optimal case for minimizing waiting time, but that required looking into the future, so we were basically going to approximate it with multi-level feedback queues. Right, so it's just kind of the same idea here. We have this nice, simple, provably optimal policy that we can't actually do because we can't see the future. So instead, we're going to assume that the past is a good predictor of the future, and just design a policy that we can actually implement that will hopefully give us close to the optimal performance. So now remember, one important thing here is, this is actually related to your question of the difference between LRU and first in, first out, is essentially whether we're talking about the time when we fetched the page from disk versus the last time we accessed the page on memory. Right, so in LRU, we're looking at pages that we were accessing recently. Right, so we may have fetched a page in the distant past, but if we're repeatedly using it, it may have been sitting in memory the whole time since we initially fetched it. So, LRU is going by access time. First in, first out is essentially just going by fetch time when we actually fetch the page from disk. Right, so that's essentially the core distinction here between FIFO and LRU. Questions on the basic policies? Now, we didn't actually talk about random. Actually, in practice, that works reasonably well to basically just randomly pick, a page to throw out. But obviously, you can't really sort of analyze much about how well that'll actually do. Yeah.
So we talked about being able to schedule processes based on priority. Wouldn't it make sense to incorporate that information into this algorithm?
So you're saying basically try to get, so the idea is to basically incorporate priority into pages. So what, like you could, I suppose, give individual pages a priority number.
Or rather, choose pages from processes with low priority first.
Yeah, you're essentially talking about the case where you have multiple processes all sharing the same physical space, right? And essentially the point being made is that if you have a process with really high priority and another process with low priority, you probably want to keep more of the pages from the process with high priority in memory versus processes with low priority. So that's actually essentially a different problem that we're not considering yet. For the moment, we're basically just talking about within a single process. Next class, we're actually going to talk about the case you bring up, which is how are you actually doing multi-programming with this and sharing the physical address space with multiple processes. But for the moment, we can just sort of assume we have one process running and we're deciding how to manage its pages in physical memory. And we don't really need to worry about, process A versus process B. We're just worrying about, page A versus page B within a single process. Other questions? Basic policies make sense? Okay, so let's walk through a few examples of this. So let's say we have 3 frames of physical memory, right? This is the fixed amount of physical memory we actually have available, so we can store 3 pages of memory at once. And let's say that our process has 4 pages of memory, 4 virtual pages of memory, right? So again, here, the process has more pages than we actually have physical memory available, and we can actually still handle that because we're using demand paging. So we can basically consider how many page faults we're going to get given a certain stream of memory addresses that we're referencing. So this is called a reference stream. So what this is saying is when we're running our process, this is the sequence of memory addresses that we're going for, right? So what this is saying is that first the process is going to request memory address A, then memory address B, then C, then A again, so on and so forth. Right? And so that's not saying anything about when page faults are happening. That's simply saying that's what the program is doing. Remember, the page faulting and all of this demand paging is completely transparent to the process itself. This is just the order of memory addresses that the process is requesting. And so our job is to basically handle the demand paging, to handle that reference stream, and ideally get as few page faults as possible. So first, let's consider this using first in, first out. So first, what we're going to have is all the frames of memory are empty, right? Because initially, there's nothing. And the first memory access that happens is A. So what's going to happen? So is page A in memory? No, right? Page A is not in memory, so that's going to cause a page fault. And we're going to bring that into memory. And so let's just say we stick that in frame 1. So here we're just essentially denoting the contents of each frame, and a star indicates that it was a page fault. So we're saying here, we requested A, wasn't in memory, so that causes a page fault, so we stick it in frame 1. So now we access memory address B, which is not in memory. So that's going to also cause a page fault. So we can load that and stick it in frame 2. Right, so frame 1 already has A in it, that's just going to sit there. Now we've loaded frame B, or page B, into frame 2. So now our memory has 2 of the 3 frames are being used. Same thing for C, we request C, not in memory, creates a page fault, we load that into the 3rd frame. All right, so now we have A, B, and C in memory. So now we request page A again. So is that going to cause a page fault? Right, no page fault here because A is already in memory. So nothing to do there, no page fault incurred. Same thing with B. B is in memory, nothing to do, no page fault. So now we request D. And D is not in memory, right? So this is going to cause another page fault. So this is where the choice of the page replacement algorithm actually comes into play. So we need to pick one of our 3 pages of memory to throw out and replace with D. Right, and so the way we're doing this in, first out, is we're just looking for the oldest page that we actually brought into memory. Which is what here? A, right? Because it was, 6 memory accesses ago we brought in A, 5 memory accesses ago we brought in B, or rather 5, 4, and 3, and so C was the most recently brought into memory. So we're throwing out the oldest loaded page, which is A. So now frame 1 has been overwritten with the value of D. That's another page fault. Question?
Yeah, so is there some sort of counter that allows you to know how long you're going to play? Because, like, for me, the easiest thing, I guess it would take more memory, but the easiest thing to see without a counter would just be B would be in frame 1, and C would be in frame 2, and then D would be in frame 3, versus, because, like, right now you have to look back in the past to see how long something's been there.
Yeah, I mean, in practice, if you were implementing this, you're obviously going to have to do some bookkeeping to keep track of what was loaded, right? So for example, you might be maintaining something like a linked list of pages that were actually loaded, and just updating the linked list every time you have a page fault to pick which page you're actually throwing out, the oldest one in the linked list.
Okay.
So yeah, you have to actually do some bookkeeping to do this in practice. But for the moment, let's just sort of disregard how it's actually happening and just see how the examples work. So now we're accessing page A again, right? And this is bad because we just threw out page A, right? And now we need page A again, so this is going to cause another page fault, and is going to replace what? So what is now the oldest loaded page that's sitting in memory? Right, so now we have D, B, and C in memory, and of the three, B was loaded the longest ago. So we're going to replace B, and now we have D. D is still in memory. B is another page fault, so we have to replace another page of D, A, and C. Obviously, the oldest one that we loaded is C, so we're going to replace C. So on and so forth. C is another page fault, and then A is not a page fault. Right, basic idea pretty clear of how we ran through that. So now we can just see, count up how many page faults we got here. We had 3 when we were initially loading the pages, and then we had another 4. So we had 7 total page faults from running this. So now let's consider how we can do this using the min page replacement policy. Right, so now in practice, right, the problem is we can't look into the future, but in this example, we can actually do that, right, because we are given the actual sequence of memory addresses that our process is actually going to request. So we can actually see how the optimal policy would do. Right, so first, same 3 things are going to happen because there's nothing in memory. So of course, we have to have page faults to load the initial 3 pages in. So now A is again not a page fault, B is not a page fault. Now we request D, and that's a page fault. So now here's where we're doing something differently. So rather than looking at the oldest loaded page, we're looking for the page that's going to be accessed furthest into the future. Right? So we have A, B, and C in memory, and A is going to be accessed 2 units in the future. B is going to be accessed 3 units in the future, or 4 rather, and C is going to be accessed 5 units in the future. So what are we going to replace? C, right? C is going to be the farthest, we're not going to use C for the longest amount of time, so we're going to evict C here, right? So this is different from what we were doing in FIFO. And now we see that here, that's going to be good for us because now we're requesting A again, and in FIFO we threw that out, so we got a page fault. Here we're not getting a page fault because it's still there, so that stays. Now we request D, still there, no page fault. Request B, still there, no page fault. Now we request C again, that's another page fault. So in this case, we have to pick from A, B, and D. Obviously A is accessed at the next time, so we're not going to evict that. So let's just sort of arbitrarily say we're going to evict B. We could obviously evict D as well. It would sort of make no difference here. And then finally, A is still there, so no page fault. Right, so we count these up here, and we see that previously we got 7 page faults. Now we only have 5 page faults. Question?
Yeah, just the last one.
Oh, yes, that should be a C. Yeah. Yes, and the top should be A. Yes. Right, so previously we had 7 page faults. Here we only have 5. And also note that, right, these 3 initial page faults are sort of unavoidable no matter what you're doing. So in some sense, we sort of have the number of page faults here, because previously we had 4 page faults after the unavoidable initial 3. Now we only had 2 extra page faults. Right, so we're doing significantly better here. But so remember, the problem here is that in order to do that, we had to look into the future. In practice, we can't do that, but we can look into the past, because we know what's already happened. So now let's look at how we do this with LRU. So here, rather than looking forward in the string of memory references, we're going to look backwards. But it's essentially the same idea otherwise. So first 3 are going to be the same. Page fault on all 3 of those to load those into memory. A is not a page fault, B is not a page fault. And now we're looking at D, right? So we can't look forward anymore. Now we're going to look backwards. So we're going to throw out the page that's not been used in the longest time, right? So we have A, B, and C to consider. So A was accessed 2 units in the past, right? B was accessed 1 unit in the past, and C was accessed 3 units in the past, right? So what are we going to throw out? C, right? Because C was the least recently used page of everything that's in memory. So we're going to throw out C. And remember, this is just sort of, we're using the past as a guess for the future. And in this particular case, we see that we made a good guess, right? Because here we did the same thing that was good in the min case. We didn't throw out page A, we threw out page C instead. Now we request A again, and so no page fault. D, no page fault, right? This is the same as what happened in the min case. B, no page fault. And now C is another page fault. So what are we going to throw out here? So we have A, B, and D. And A was 3 in the past, B was 1 in the past, B was 2 in the past. So we're going to throw out A. Now here we see that that was actually a bad guess, right? So this is showing that in general we're expecting LRU to be a good approximation of min, but it's still just an approximation. We can make bad guesses. So in this case, that was a bad guess, because the very next page we access is A, which we just threw out. So we're going to incur another page fault to load A back in. Right, so in this case, we sum those up, and we got 6 page faults. Right, so that's still better than the 7 we got in FIFO, not as good as the 5 we got in min. But in general, because of locality, we're going to expect that the same couple of pages are going to be accessed repeatedly. So in practice, LRU is going to be a pretty good approximation of min. And since we can't do min, obviously, LRU is sort of the next best thing we could use. Questions on how LRU is working? Make sense? Okay. So one question we can ask is, when is LRU going to actually do badly? Right? So what are sort of the cases when it's going to do badly? So let's consider this is a different string of memory addresses when we're just going to say ABCD, ABCD, ABC, when we're sort of just using every memory address. So let's see what happens here. I'll go through this a little quicker, but basically we'll have the same 3 things here, 3 page faults, and now D, not in memory, going to cause a page fault. So what are we going to throw out? Right. So we're going to throw out A because that was the least recently used page. That was 3 ago. We last used that. Now A, we just threw out, so that's going to be another page fault. So we're going to replace B. Now we access B, which we just threw out, so page fault, and so on and so forth. And so every single one of these is actually going to cause a page fault. Right? So if we do this, we got 11 page faults. Every single one was a page fault. We did terribly. So basically the reason for this is, this gets back to the idea of the working set. Right? Because what is the working set is basically the set of memory that your program is actively working on right now. So that's sort of the set of pages that are being accessed repeatedly. And the point is that because of the 90-10 rule, we expect that working set to be small in general. So we have, of course, in general expect that working set to be able to fit in memory at once. So in this case, sort of what is the working set? We have 4 virtual pages, and what's the working set? What are sort of the pages that we're actively working on over and over again? Right, A, B, C, D, it's all of them. Right, so the working set here is basically 4 pages, which is bigger than physical memory. Right, so the whole point, the sort of implicit assumption we're making in demand paging is that we can fit that working set in physical memory, access the same few pages repeatedly, and it'll all be in memory. But if the working set is actually bigger than the amount of physical memory, then we're still potentially doing really badly because we're repeatedly requesting pages that we don't have room for. Right, so this isn't so much an example of LRU being a bad algorithm. It's more an example of the idea that the working set in general is expected to be small and fit in memory. So what we're expecting most of the time is we have a bunch of processes with small working sets, and all of those working sets can fit in memory at once. And then the parts of the process that are not in the working set can be safely sitting on disk, and it's not going to cause too many page faults. Right, so that's essentially the point here. All right, so if this working set were smaller, if it were, say, rather than doing A, B, C, D over again, if we were just doing, A, B, A, B, A, B, A, B, then the working set is only 2 pages, smaller than physical memory, and that's, not going to really cause any page faults here after the initial 2, because we can fit it all in physical memory. So, now let's consider what happens when we're actually adding memory. Right, so in general, if you have a system that has some amount of physical memory, and you go and add more memory, what do you expect to happen to the number of page faults? If you give your machine more memory, should you page fault more or less? Less, right? Obviously, I mean, the idea of a page fault is when you don't have enough physical memory to store everything, you're incurring page faults to swap things in and out. So of course, if you take your machine with some amount of physical memory and give it more, you of course expect to get fewer page faults than you did to begin with. So let's look at an example of that. Let's say we're using FIFO again, and let's say we have this string of memory addresses, and we can consider 2 scenarios, one where our machine has 3 frames of physical memory, and then the same string of addresses with the same reference string where we have 4 frames of physical memory. Right, so these are just sort of 2 scenarios with 2 different amounts of memory. So let's see how that works. So, let's do the top first. So same thing here. The first 3 are going to fault. D is a fault again. We're going to throw out what? Remember, this is FIFO, so we're throwing out the oldest loaded page, which is A, right? A is another page fault. We're going to throw out the oldest loaded page, which is B. So on and so forth. Throw out C. E is another page fault. Throw out D. So on and so forth. You don't need to belabor the details here, but just basic FIFO. So we run through this, and we got 1, 2, 3, 4, 5, 6, 7, 8, 9 page faults, right? 9, right? Yeah. So 9 page faults there. So now let's run through the same example with 4 frames of physical memory instead of 3. Right? So page fault, page fault, page fault, page fault. Now A is already there, B is already there, E is a page fault, so we're going to throw out A again. A is a page fault, we're going to throw out B. B is a page fault, so on and so forth. And how many page faults did we get here? 10. So does that make sense? Right, so what happened to the number of page faults by adding more memory? It increased, right? We had 9 page faults with 3 frames of physical memory, so we gave our machine more memory to use, and then we got more page faults. Right? So there's actually a term for this. This is called Bellidy's anomaly, which is basically that adding page frames in some cases may actually cause more page faults than if you had less memory. And in general, that's going to be a property of certain types of page replacement algorithms, of which FIFO is one. So FIFO is one such algorithm where adding more memory may actually make you do worse. Question? Well, in practice, you're not actually going to use a FIFO approach. So, if the question is in a real-world system, I guess the answer is, well, you don't really do FIFO. But this sort of just generates, this is sort of a very counterintuitive notion that adding memory to your system may actually make you do worse in terms of the number of page faults you're hitting. But now we can actually look at this with LRU. We don't need to run through the examples, but I've just put them out here. So if we do this same sequence of the same reference string and the same 3 and 4 frames of memory using LRU instead of FIFO, we're going to get 3, 6, 9 page faults with 3 frames of memory. And with 4 frames of memory, we're going to get 8 page faults. Right, so we did actually go down there, which is sort of what we would more expect. So actually, LRU does not have that issue that we had in FIFO. Adding more memory when you're using LRU is always going to decrease the number of page faults. Now, can anyone see why that might be happening? So take a look at, in each of these cases with 3 frames and 4 frames, take a look at what the actual pages in memory are at each point. And what does anyone notice about the difference between the 3-frame case and the 4-frame case? Right, so at any point in time, there's 3 specific pages of memory sitting in 3 specific pages sitting in physical memory in the 3-frame case, and 4 specific pages of memory sitting in the 4-frame case. And what's the relationship between the set of 3 and the set of 4? Yeah.
The set of 3 is always a subset of the set of 4.
Right, exactly. In any case, at any point in time, the set of 3 frames that are the set of 3 pages in memory, say here it's D, A, and B, are always also present in physical memory in the 4-frame case. So here we have D, A, and B in the 3-frame case. We also have D, A, and B here. They're in different frames, but that doesn't matter. And then we have an extra frame that's being used to store something extra. And that's true at any point in time in here. Over here we have E, A, and B sitting in memory. Here we also have E, A, and B, and then the addition of C. Right? So this is illustrating basically why we can't be doing any worse, because LRU, as you give it more frames, is always going to have the same set of the most recently accessed pages plus some extra sort of older pages. Right? So in the 3-frame case, we're basically storing the 3 most recently accessed pages in memory at all times. So in the 4-frame case, we're also storing the 3 most recently accessed pages, and in addition, we're storing the 4th most recently accessed page. Right? So that's always going to be a superset. It's always going to include everything that was stored here. Right? So see, basically, by the way the LRU is operating, adding memory is always going to make it do better, or at least no worse. Make sense to people? People see how that's working? Right, so we don't have to worry about adding memory making things worse in the LRU case. So now let's consider, so we sort of made the argument that LRU is sort of a reasonable algorithm that we can actually do because we don't have to look into the future. But we haven't actually said anything about how we can actually implement that in the OS. So what might be one way we can actually implement this where when we want to evict a page, we're going to pick the least recently used page? What sort of one simple way we could do that? Any ideas? Yeah. So keep a queue, and whenever you have a page fault, put it on the queue and throw out the older one. Right, so actually what you're describing is how you would do FIFO, right? Because what you're describing is when you're throwing out the last loaded page. Remember, and that's the core distinction between FIFO and LRU. LRU is going by when you used a page, not when you've loaded it. Yep. Right, so you want to keep track of some count. Well, not how long it's been in there, meaning what? Right, so you basically want to track how long each page has been since it was last used. Right, so what might you actually store with each page in order to keep track of when it was last used? Yeah.
Something is used, and that particular one is used, it's just reset to 0.
So that's basically a clock, right? It's basically a timestamp. Right, so all you essentially would need to do is store a timestamp with each page saying, this was when I last used the page. Right, because if you have a timestamp with every page saying, this was the last time I accessed it, then it's easy to figure out what the least recently used page is. You just check the timestamps, pick the oldest timestamp, and evict that page. And whenever you access a page, you can update its timestamp. Right, pretty simple idea. Just use the timestamps. So that's basically what we call perfect LRU, which is implementing exactly what we described, least recently used. You can just keep a timestamp for each page, And in that timestamp, store the time of the last access. And then when you need to throw one out, you just check those timestamps and throw out the least recently used page. So what might be some problems with doing it that way? Yeah. Right, great. That's one problem, is when you are actually doing an eviction, you have to go through every single page and look at every single one in order to determine what the least recently used page was. Right, so that's sort of one key operation, is page eviction. Now, what's sort of the other key operation we need to consider? Right, so one thing that's happening is pages are getting evicted, right, and the other thing that's happening is that pages are getting accessed, right? So what are we needing to do here when we access a page? Yeah. Right, so every time we access a page, we're also having to record the timestamp, right? And that might not seem like much, but remember, this is, again, going back to, remember when we were talking about page tables? Page tables are stored in memory, and we don't want to have to access the page table every time we do a address translation, because that's potentially doubling the speed of memory accesses if we have to access memory twice. Right, so this is sort of the same idea, where every time we're accessing memory, we're having to record a timestamp. So that's potentially quite expensive, because we are, of course, having to store those timestamps somewhere, probably in memory, say within the page table. So we're, again, having to go into memory and do something every time we access memory. So that's also expensive. So, for both of those reasons, that approach is basically not efficient enough to be able to do in practice. It'll make your memory access time way too slow, both for memory access itself and also when you need to do a page fault. So we could, consider another approach where, let's keep a list of pages and, just essentially as we access pages, just move things around in, the linked list. Any problems there? Right, because if we do it that way, then at least we don't have to loop through all the pages to find the least recently used one if we're essentially just keeping, an ordered list. So that might solve sort of the problem of having to look at every page. But what are we still having to do whenever we do an access? Yeah.
Go to memory and move stuff around.
Right. We're essentially, to update that list, we're still essentially changing a bunch of pointers. And again, doesn't seem like much, but we're talking about doing this on every single memory access. Maybe if we were just having to do that on page faults, not a big deal, because page faults are happening really infrequently. But if we're having to update a bunch of pointers in memory every time we access memory, that's also very, very expensive. So we essentially can't do that either. So in practice, we basically don't use perfect LRU. So instead, we're basically going to approximate LRU. Right? This is sort of a running theme. Every time we have some nice, perfect approach, can't do it efficiently enough, we're going to use some approximation instead. So the idea here is, rather than storing exact timestamps, we're basically going to store some approximation of actual timestamps. Right? So let's say that normally a timestamp might be a fairly long string of bits, if you're considering storing it in memory. But let's say we're just going to use, like a 2-bit timestamp. So if you have, a 2-bit timestamp, then, you might have, your values, the potential values of the timestamp are, 1, 1, 1, 0, 0, 1, and 0, 0. We're just going to use a few small bits. And the timestamp is basically, again, going to do what we want, indicating when a page was last used, but it's just going to be an approximation. So just to give sort of a very simple example, let's say that, this value indicates that, the page was used in the last 5 minutes. Maybe this value means it was used in the last 10 minutes, so on and so forth. Maybe this was the last 15 minutes, and that was, prior to the last 15 minutes. Right, just sort of a simple example. So we're not going to be keeping an exact ordering of when every page was used. We're just going to basically partition them into pages that were most recently used. There'll be a bunch of them sitting with this timestamp. Now, of those, obviously, some will have been accessed more recently than others. but we are essentially saying we don't need to be exact. We just want to get a good approximation. So we can just use a few bits to get some approximate timestamp. Question?
Yeah, so I just want to make sure I understand. So if you're, between time 0 and time 5,
Yeah.
You might give every single one, 1, 1.
Exactly, right. So every single page that has a timestamp of 1, 1 meant it was accessed sometime in the last 5 minutes. You don't know exactly when, because that's why it's an approximation. But those are still, you know that they were accessed more recently than anything in this group, or that group.
Okay. So if you're doing it like that, and then so between 5 and 10 you write 1, 0, and between 15 and 20 you write 0, 0. When you get back to 21 and 25, would you go back to 1, 1? Like would you start printing 1, 1 again?
You basically have to do bookkeeping to periodically, say 5 minutes has passed.
Yeah.
Say you just used this, so it was just used, and now 5 minutes passed. So it should be in this group instead of that group.
Yeah.
So you're going to have to actually go in and update one of the bits to basically shift it down. So periodically, essentially, everything is going to move from one group to the next. And as you access things, they get put into the most recent group.
So doesn't that still kind of have the same issue where, not as frequently, but you still have to go back into memory?
Well, see, the key point here is that by using this approximation, where we're just going to use basically a small set of bits, then if we're only using a small set of bits, we can actually do this in hardware.
Okay.
Right? So the point here is that if we're not keeping an exact full timestamp, if we just have a few bits per page, then we can do this in the TLB, essentially. So we can end up doing this in hardware. So, this is going to be an approximation, but because you're essentially only operating on single bits, this is going to be a lot faster. But, we still potentially have the problem of you have to do a search through all the pages when you actually have a page full. So, as I said, the way we can actually do something like this is by, adding a few bits to the TLB so that you're not having to go to memory every time. So, now in practice, we're actually going to do something even simpler than this. So this scheme is sort of called the additional reference bits approach. And in practice, we're going to do it even simpler, and we're just going to use 1 bit per page. That's it. Sort of like a 1-bit timestamp. So the idea is, this is called the second chance algorithm, or the clock. So we have all of our frames of memory, and we're going to keep them in some circular list. And so pages of memory are being accessed, and every page has a reference bit, 1 single bit. So when we reference a page of memory, we're going to set its reference bit to 1. So as things are getting accessed, the reference bits are always getting set to 1. And when we get a page fault, we now need to pick something to throw out. So this is basically going to be like a clock, where we have frames of memory arranged in a circle, and this is like a clock, and we have a clock hand pointing to one of these pages. And each one of these has a reference bit that's either going to be 1 or 0, depending on as things are accessed, the reference bits are getting set to 1. So what we're going to do is when we have a page fault, we're basically going to advance the clock hand looking for a page with a reference bit of 0. Right, so if we get a page fault here, clock's currently pointing here, that has a reference bit of 1. So we're not going to evict that. We are going to set its reference bit to 0, and then advance the clock hand here. This already has a reference bit of 0, so we're going to pick that page and throw it out to bring in the new page. Right, so as the clock is going around, as it hits pages with a reference bit of 1, it sets them to 0. And if you hit a page with reference bit 0, you evict that page and bring in the new one. And of course, the new one that you bring in will have a reference bit value of 1 because you just used it. Right, so this is sort of why this is called the second chance algorithm. Right, because you're basically saying that as you pass every page, you're basically giving the page a second chance to be used before you decide to evict it. right? Because as your clock is advancing, once you get back to a page that has a reference bit of 0, what does that mean about when the page was referenced or not referenced? Yeah. Right. It means that you went through the entire ring of pages, and that page was never actually used. Because if the page had been referenced, it would be set back to 1. So when the clock hand came back around to this page, it would set it to 0 and continue going. Right? So if you have a page that's repeatedly accessed, you're going to keep setting its reference bit to 1, and you're very likely not ever going to actually evict it, because every time the clock gets back around, the reference bit will be set back to 1. So I think we're out of time, so we'll stop there.